Good afternoon, dear colleagues. My name is Ostap. I am a PhD student of Department of Organic Chemistry at Lviv Polytechnic National University, and also of Department of Molecular Biotechnology at Ghent University. And my two supervisors are Professor Yuri Stetseshin and Professor Andres Kirtech. And today I would like to present my research work about grafted polymer brushes. It's a protein orientation in embedded nanoparticles for biomedical application. My presentation will last about 15 minutes and divided into three following sections. First, I will give you some background on grafted polymer brushes. Then I will focus on the properties of our brushes. And finally, we will look at the application of polymer brush. Over the past few years, several polymers and polymeric composites responding to stimuli such as oxygen, temperature, light, solvents, power of solution, or pH have been developed. And a range of responsive polymers, including brushes, thin films, gels, nanofibers, have been effectively fabricated. They demonstrate great potential in industrial applications, such as coatings, sensors, electronic devices, and also in biomedical, including tissue engineering, antibiotic, drug delivery, and other. Smart polymers can change the properties under the influence of various factors. In our work, mostly we choose temperature-responsive polymer brushes. Temperature-responsive polymer brushes consist of surface graph. And this effect may be driven by different mechanisms, including the transition from glassy to rubbery state or from pneumatic to the isotropic state. How to fabricate polymer brushes? Commonly, there are two basic methods of creating brushes. It's grafting to and grafting from. In general, grafting to strategy is described as a reaction between the end functional site macromolecules and the solid surface. It includes methods which require plasma treatment and electron beam, ultraviolet light irradiations, and the multifunctional surface modifiers. But this approach can't be used to produce thick and very dense polymer brushes. In turn, in the grafting from technique, the polymer chain is grown from the pre-modified surface in a two-step procedure, including grafting multifunctional surface modifiers to the solid surface, followed by fabrication of the grafted polymer brushes coating using surface-initiated radical polymerization. Also, this method allows a better control of some properties, such as grafting density. It remains difficult to establish in large surface areas and unprotected atmosphere, and this method, we use this approach in our work. Okay, in this slide, you can see a scheme of this methodology. The grafted polymer brushes attached to glass are fabricated in a three-step process. On the first stage, we fabricate amino functional site substrate. On the second stage, initiate graft. And the third stage, polymerization our brushes. Third stage shows on the slide. In a flex, methanol, water, and monomer are mixed and deoxygenated by bubbling through nitrogen for 10-15 minutes. Add catalysts, and the headspace purged with nitrogen again. The solution is treated over the substrates in the deoxygenated tubes. And after the desired polymerization time, samples removed and washed with methanol and water. And typically, this method produces a polymer draw rate of approximately 5-10 nanometers per hour. I want to present you three of my past projects. First is temperature-controlled orientation of proteins on temperature response in grafted polymer brushes, such as polybutyl mesacrylate and polybutyl acrylate. The composition grafted brush coatings were determined using time of flight secondary mass spectroscopy. This is representative positive ion-of-sim spectra, which confirmed that polymerization was successful. The contact angle were measured for PBMA grafted brush coatings with thicknesses of 43 and 80 millimeters, as well as for PBA with thicknesses of 38 and 65. This character. The alpha data from the PBMA grafted brush coatings suggest the transformation of the surface morphology from very raw and structured to relatively smooth at an increased temperature. For PBA coatings, no morphological changes at different temperature were observed. And the RMS values estimated confirm a morphological transformation for the PBMA coatings. Based on our experimental data, we propose a hypothetical scheme for the temperature sensitive of the PBMA and PBA grafted brush coatings at temperature close to the physiological limit. At temperature less glass transition temperature, PBMA grafted brush coatings are in a glassy state with polymer chains. In contrast to the glassy state, at temperature more glass transition temperature, the properties of the PBMA grafted brush coatings are essentially different. The studied temperature interval for PBA grafted brush coatings is far from glass transition temperature, and we shall state that the PBA coatings are in a rubbery state. Fluorescent labeled BCA was used to study the protein adsorption. For PBMA coatings, protein adsorption depicts a strong temperature dependence and increases almost twofold. In contrast, for the PBA coatings, protein adsorption almost displays no temperature dependence. That's why further studies were performed for this type of brushes. BSA consists of three domains, albumin 1, 2, and 3. Therefore, it's a very conventional object to study protein orientation. BSA adsorbed to PBA coatings below temperature, glass transition temperature, adopts such an orientation that albumin 1 and 2 are exposed out of the surface, whereas for temperature above transition, albumin 3 is exposed. The control of the orientation of proteins plays important role in obtaining the good steric accessibilities of active binding sites and increasing stability. Next project is this combination of polymer brushes with nanoparticles, such as uniform calcium carbonate nanoparticles embedded in polymer grafted brush coatings were synthesized using precipitation from solution calcium chloride and sodium carbonate. The top sim spectra contains the peaks characteristic for polymer and the peaks from calcium carbonate nanoparticles. This is FM data and the SAM photo. The SAM images recorded for samples with calcium carbonate nanoparticles incorporated in polymer grafted brush coatings demonstrate uniformly distributed calcium carbonate nanoparticles, the square shape. Their size did not exceed several tens of nanometers. It is well known that calcium carbonate nanoparticles during synthesis form a mixture of butyrate and calcite forms, and the ratio between these forms depends on the conditions of the synthesis. In addition, the butyrate usually transforms to calcite, which is a more stable calcium carbonate polyformic form, represented cubic crystals and depicted in this photo. Incorporation of the calcium carbonate strongly transforms the structure of coating from relatively smooth to more structured with good expressed at large elevations. An impact of the low concentration of the embedded calcium carbonate nanoparticles on cells adhesion and growth depends strongly on the type of studied cell line. Human scan cells, melanoma, and osteoblastics. And it can be postulated that the impact of polymer and polymer grafted brush coatings with a low concentration of embedded calcium carbonate nanoparticles strongly depends on the type. In contrast to the non-adhesion properties of polymer-based coatings reported before, we did not find difference in cell adhesion for 24 hours of the incubation on control glass surface and polymer coatings for the all studied cell lines. Based on the temperature responsive properties of grafted brush coatings and calcium carbonate nanoparticles as a material with a controlled release of the biological activity substance, we believe that the future research will allow the development of new platforms for tissue engineering with improved growth of cells due to both the presence of nanoparticles and release of the biologically active substance from calcium carbonate nanoparticles. And the last one thing, polymer non-composites with silver nanoparticles. Glass plates with grafted polymer brushes were dipped in silver nitrate solution with different concentrations for different times, undergone flow. Recorded results show that nanocomposites coating with embedded silver nanoparticles, especially the ones prepared after 30 minutes immobilization in silver nanoparticles, in silver nitrate, are more hydrophilic than the pure polymer coating. To study the influence of silver nanoparticles on the morphology of the coatings, IFM analysis was performed for tests and polymer coatings with different grafting polymerization. This slide demonstrates cultivation of two types bacterial strains on the petri plates after incubation with the polymer-based nanocomposites and the polymer control samples at 7 degrees. At 37 degrees, almost no bacteria were visible for temperature-responsive coatings with silver nanoparticles, whereas the growth of bacteria remained unperturbed for pure coatings, indicating well-expressed temperature-dependent antibacterial properties for silver nanoparticles integrated into our brushes. Silver nanoparticles embedded in polymer brushes do not have any cytotoxic effect towards the human skin cells for short exposure time, and the amount of the melanoma cells is slightly decreased on node surface containing the silver nanoparticles. Maybe I will not read the conclusions. Але в двох словах ще розкажу, в чому суть роботи, що ми створювали три типи різних шарів. Це є трьохстадійний процес. Перший – це передня аптеза, другий – це є поширення ініціатора і, власне, третя стадія полімеризації. Перша робота була зосереджена на орієнтації білків на температуру чутливих полімерних щитах полібутилметакрилату і полібутилакрилату. Друга робота була зосереджена на дослідженні властивостей нанокомпозиту з наночастинками кальцію СО3, а як полімерна основа виготовлялася поліоліготиленгліколь-метакрилатова поверхня. І в третій роботі, знову ж таки, створювалася поліоліготиленглікольова метакрилатова полімерна щітка вже з наночастинками срібла. І як висновок, там можна сказати, що ця поверхня була нецитоксичною і антибактеріальною з температурочливими властивостями. І хочу висловити подяку своїй альма-матері, Львівській політехніці, кафедрі органічної хімії, з керівником кафедри професором Дончаком та моїм співпрофесором професором Стецишиним. І дякую за співпрацю Гентського університету, кафедри молекулярної біотехнології на чолі з професором. Також дякую Ягелонському університету і кафедрі молекулярної та міжфазної біофізики на чолі з професором Будковським за кооперацію. Дякую вам. Вас не чути. Вас не чути.
Дякуємо, пане Остап. Які будуть запитання? Я так зрозумів, що можна задавати і англійською, і українською. Будь ласка. Людмила Васильівна, будь ласка.
Explain, please, if you have any information how the morphology on surface influences the cell bacterium on the surface. You have shown the IFM investigation with different morphology of surface and how this different morphology influences the cell adhesion on this surface.
Yes, okay. Thank you for your question. Yes, when we have, for example, temperature, more glass transition temperature, we have very raw and structured smooth. And for this type of our brushes, cells adhesion more less because it's our surface more hydrophobic. When we have a temperature more glass than this temperature, is our surface more hydrophilic and cell adhesion is better.
And additional question, hydrophobic and hydrophilic surface have different morphology of your brushes?
Yeah, yes.
Yes. Okay, thank you.
Спасибо.
Можу я запитати?
Так, будь ласка.
Я запитаю українською. Скажіть, будь ласка, а от на слайді 12, там, де ви говорили про орієнтацію протеїнів на поверхні, на полімерних поверхнях різних. І там ви, я так зрозумів, що ви оперуєте тим, що більше ТЖ і менше ТЖ. А скажіть, будь ласка, а вплив температури саме на орієнтацію самого протеїну, не на безвідносно до полімеру. Протеїн же теж змінює свою фізико-хімічну, якусь фізико-хімію, можливо, конформацію трошки у відгук на температуру. Ви це враховуєте?
Дивіться, тут такий нюанс, що цю орієнтацію сама адсорбція проходить при різних температурах. Сама адсорбція білка в різних температурах, а досліджується вже орієнтація при температурі кімнатній. Тобто, перше, матеріал, білок адсорбується на поверхні при температурі, наприклад, там було при 10 градусів і при 36 градусів. Пройшла адсорбція, і тоді вже з допомогою мас-спектрометра ми досліджували адсорбцію при тих різних температурах, а це вже була температура кімнатної.
То у вас головний фактор більше ТЖ чи менше ТЖ, тобто стан полімеру? Чи все-таки...
Так, це стан полімеру.
Мені здається, що цього недостатньо. От. Ну, добре, дякую.